Well, we're going to start talking about angular momentum, which is our penultimate interesting topic. And we're not going to get to the principle yet because we have to figure out what angular momentum is before we actually start talking about it. So here is the basic idea. Let's consider something going around in a circle at constant speed. Yeah, Ferris wheel in this case, vertical. So here's this thing going around at constant speed. So let's concentrate on one. We can call this a person riding on a Ferris wheel, the blue dot. Okay, is that person's momentum changing or not? Yes, it is, isn't it? So we can attach an arrow. And we see that because it's at constant speed, the magnitude of the momentum isn't changing, but the direction is. Now, that feels kind of unsatisfying. You want to say, okay, the momentum's changing, but something's constant. Just saying, well, the magnitude of the momentum is constant isn't really satisfying because you want something about going aroundness being the same. And we don't have a way to talk about that yet. Unfortunately, also, pretty much anything we can think of to display is changing. So that's the position vector of that person relative to the center of the Ferris wheel. That's, of course, changing too in direction as the Ferris wheel rotates. But if we look at them together, it seems like there might be something about those two vectors and their relationship to each other that isn't changing. Yeah, the angle between them. So the magnitude of the momentum isn't changing. The magnitude of the position vector relative to the center isn't changing. The angle between the vectors isn't changing. So maybe we could write the thing that isn't changing here as some product of those things. So suppose we said that we were going to multiply the magnitude of the momentum, the magnitude of the position vector, and some property of the angle between them. We'll call it sine. And we say if the angle is not changing, that thing would be constant. Now, there's a piece of information missing in this, though, because what if it were rotating at constant speed in the other direction? Well, position vector would have the same magnitude, the momentum would have the same magnitude, the angle between them would have the same magnitude. So there's not enough information here. And so we need a mathematical way of encoding it. So we could say, well, it's going, I always have to think counterclockwise, right? So it's going, so we could say, we know that number, and it's going counterclockwise. And the problem with that is that somebody standing on the other side of the Ferris wheel is going to think it's going clockwise. So therefore, to communicate with them, you're going to have to say, well, if I'm standing, we have to agree on an origin and now a coordinate system, and I'm standing on the plus z-axis, and you're standing, and so then I see it clockwise. So one way of specifying direction is notice that these vectors are in a plane, right? So they're in the same plane. One way of specifying the plane is by telling somebody what a unit vector perpendicular to that plane is. And so there's a right-hand rule of this kind where we say, okay, if I curl my fingers in the direction that this is going around, and I stick my thumb out, and I use my right hand, then if I tell you that vector, you know which way it's going. I have to use my right hand, though. So we were working on a right-handed coordinate system. So we could say that this would be the magnitude of something. So this turns out to be what we call the magnitude of the angular momentum. And we usually call this R sub A because just to remind us that we have to specify the point that R is starting at. And if you curl your right hand fingers in the direction of rotation, your thumb points in the direction of a vector normal to the plane, and so we call that the direction of the angular momentum. So angular momentum actually can be represented by a vector. Its magnitude would be the magnitude of r times the magnitude of momentum times the sine of the angle, and then the direction is what you get with your right hand, curling your fingers around in the direction of rotation. Now, we're going to need something a little more mathematical than that eventually, because curl your right hand is hard to put into an equation, but we'll start with that. So we've got a planet going around a star, and its orbit is in the xy plane, and the momentum is shown by the red arrow. So what would we say the direction of the angular momentum of this planet is? We say relative to the star, because the star is the point we're picking to draw r from. So we start talking about angular momentum and vectors of this kind. It really is going to be necessary to remember to bring your right hand to class, but also to be willing to use it. So if you feel like it's sort of embarrassing and you don't really want to move your hand very much, that's not going to work. So we all have to wave our right hands around a lot, and that's just the way it is. So we'll all look silly together, but we'll get the right answers. Okay. 4 out of the page. Yep, that's right, because we're curling our fingers in the direction of rotation using our right hand. Thumb sticks out toward you. Formal here, so the usual coordinate system. Here's a planet going around a star the other way. So what is the direction of its angular momentum? So remember the usual coordinate system, positive x to the right, positive y up, z-axis out toward you. So that's a really good question. So the question is, if it's not going around, it's not revolving, would the angular momentum be 0? And interestingly enough, the answer is not necessarily. And so we'll get there. But let's get the simple ones first. Okay, let's see what you said. All right, so you said 6, which is minus z, which is into the page. So good, right? Okay. So not everything goes around in circles, though. So what if an orbit isn't circular?